molecular orbital theory. The atomic orbitals combine or interact to produce the molecular orbitals. Okay, the atomic orbitals combine to give, okay, interact or combine to give molecular orbitals. So hence, like basically call molecule is basically group of atoms, right? So molecule has a group of, like let's say two atoms combined to give, we call it as molecule. So atomic orbitals combine or interact to give the molecular orbital, or to say like another term which you have to say, suppose if there are two atoms combined, how many molecular orbitals? You will be always have two orbitals. So it depends like how many atomic orbitals you start with, the same number of molecular orbitals you will have. Okay, and again like we can use the same quantum theory and to solve this like orbital energies and shape, size, everything we can do the same thing with using the Schrodinger equation. Okay, but we are not going to see that in detail. But what advantage of this is that over like the other theory, like valence bond theory, okay, where we basically say that like the electrons are shared between the two atoms to form a molecule, whereas this one helps in telling in more like about the properties also. Okay, not only just that the two molecules are formed by two atoms combined, but it also talks about the properties associated with molecules. That's the advantage of molecular orbital over the valence bond theory. Okay, so now in the just before we saw that, okay, how the wave function, okay, for a hydrogen atom, right? So now we are going to see the hydrogen atom when they basically try to combine. Okay, so that is basically diatom molecules is going to interact. Okay, diatomic molecules are going to interact. When they interact, okay, there are two ways to interact. Okay, one is okay, one is constructive interference, another is destructive interference. Okay, so the two atoms, the wave function are going to interact. When the wave function interact, you can have constructive interference and destructive interference. The constructive interference we call it as bonding orbital or bonding molecular orbital, and the destructive interference and the orbitals that are formed as called anti-bonding molecular orbital. Okay, so now this approach, okay, is called linear combination of atomic orbitals. Okay, so just like linear combination of atomic orbitals. Okay, let make it capital A, a linear combination of atomic orbitals, okay, to produce molecular orbitals. In short term, we can call it as LCAO MO. So sometimes they say LCAO, okay, or you can basically say LCAO MO as well. Okay, so this approach is called LCAO approach or LCAO MO approach. Okay, so basically there is going to be constructive and destructive and forming a like a bonding molecular orbital and anti-bonding molecular orbital. Okay. Okay. So now we have simple model like hydrogen. Okay. So I have 1s, two hydrogens, 1s, another is 1s. To differentiate, I'm calling it as 1s A and 1s B. Okay, so these are two atoms, the nucleus and the electrons around it. Okay, so now they are going to overlap. Okay, so let's draw that. Okay, like this. So it is going to, so this is the energy of these atomic orbitals. The atomic orbitals, okay, when they basically try to combine, they form molecular orbital, right? That molecular orbital, okay, basically stabilize the molecule more. That is the preference for it. Okay, it has to stabilize so that it can be formed. So now when these two atoms combine here, okay, they form a consecutive interface and the orbital energy will be lower. So this will be called sigma orbital, okay, or bonding molecular orbital. I write like MO meaning the molecular orbitals, just for convenience I'm writing like that, but when you write it fully, bonding molecular orbital. Okay, so here these two atoms overlap like this and the electron density is like this. So I have two nucleus like this, so they have a bond and the electron cloud is around that two nucleus like this. Okay, now so this belongs to 1s A and this belongs to 1s. Let's write it down. That's general way of. So 1s A and 1s B, and they two combine to form a bonding orbital. This is by constructive interference. Similarly, there is a destructive interference. This is called sigma star. So this is sigma star. This is anti-bonding molecular orbital. Okay, and here the orbitals will be like this. See, these are two nucleus and there won't be any electron cloud between around the bond. Okay, this is the atom A, atom B. Okay, when they combine, there is no electron cloud. This is anti-bonding. Whereas here you can see the electron cloud, okay, between the bond. Okay, so kind of the bonding will try to help the formation of bond between the atoms, whereas anti-bonding try to undo the bonding, means it will act against the bonding. Okay, so we know like for a so we know the wave function, okay, for a 1s. Let's say for a simple case here I am calling it as psi of 1 psi of 1 is A and this is psi of 1 as B. Okay, so now the wave function for this one will be sigma 1 by root 2. So this one has to solve, like, but we are just directly writing it. Okay, it means it's beyond our scope of syllabus, so we don't need to worry about that. Like, so we write directly like the wave function of this bonding orbital as psi 1 as A plus psi 1 as B. So this is the sigma orbital formed by constructive interference between the wave function, and similarly this wave function can be given as sigma star 1 by root 2 psi 1s A minus psi 1s B. Okay, so this is the destructive interference of these two wave function which gives the antibonding. Okay, so now you understand how this atoms can be. Okay, so now one can also fill the electron. So let's say hydrogen. Okay, simple hydrogen. Okay, so I'll, since I said like 1s A 1s B, let's like not draw or do it on that. Okay, so I have 1s 1s, okay, from hydrogen. They combine to form sigma and sigma star. So how many atoms in 1s hydrogen? 1s 1. Okay, 1s 1. So now I am going to fill the electrons in the molecular orbital. When I put the molecular orbital, what I have to do is first fill the lowest one. Okay, like this, 1s 1. Okay, and the other electron here, 1s 1 here. Okay, so the two electrons will be in the bonding sigma orbital. Okay, and the two electrons will be in the bonding sigma orbital. This is for hydrogen. Okay, now this is a empty, right? So now what we call this orbital as, okay, another name. Okay, it doesn't matter which here or even in the higher energies, but the one with the occupied electron as HOMO. Okay, we call it as HOMO, that is highest occupied molecular orbital. Highest occupied molecular orbital. This one is empty, so we call it as lowest unoccupied molecular orbital. So this is lowest unoccupied molecular orbital, and this is highest occupied molecular orbital. Okay, this is with respect to the molecule. Okay, so this is like hydrogen, this is H2. Okay, this is the HOMO and this is the LUMO. One can also find the like through the quantum mechanical approach, one can also find the higher energies. For example, like I have like 2s means, similarly one can also find where is the 2s orbitals. Okay, the sigma bonding and sigma star bonding will come here, but it will be empty. Okay, so these are the belongs to 2s. So this is 1s 1s, so this is 2s 2s. Okay, so this can be also one can find. Okay, okay, so this is like a simple atom. Okay, like hydrogen. Similarly, one can also study other molecules. Okay, other molecules like still, let's say even diatomic itself. Okay, now we can say there are two types of diatoms like which has same nucleus as homonuclear diatomic. The other as heteronuclear diatomic. That is, both the atoms are same, the nucleus are same. Like for example, hydrogen, fullerene, chlorine, etc. So two identical atoms combine to form a molecule. This will be hetero, so it will be different. HF, CO, NO, etc. Okay, these are heteronuclear diatomic. Oh, let's go and see one by one. Okay, let's take F2 like fluorine from the homonuclear. Okay, and try to see that. So when I mean like one can also hypothetically find what is this orbital can combine from 2s of hydrogen can combine to give sigma and sigma star. It also means like we can also find the what is the orbital shape, size, everything. Okay, so by the quantum mechanical approach. Now Fullerene. Okay. So now for Fullerene, Fullerene is 1s2, 2Fa. Fullerene is what is the electronic configuration? 1s2, 2s2, 2s2, and 2p5. Okay. Second, let me see whether I can edit. Okay, so see this here it is wrong. Okay, it is only one electron. Okay, like this. Okay, now I have 1s2, 2s2, 2p5. Okay, so now when I draw that, okay, the 1s orbitals, okay, you have 1s2, okay, so 1s2 1s orbitals combine to form this Fullerene, okay, and their energy levels, okay, seems to be same as that of the atomic orbitals. The 1s energy orbitals is similar to the atomic molecular orbitals. The molecular orbitals of F2, okay, formed from 1s are of same energy as this of 1s, okay, and basically it has nothing influenceable in terms of like what happens here. Okay, so these orbitals, okay, these molecular orbitals formed from here are called as core molecular orbital, core molecular orbital. Whereas here, whatever like these 2s combined to form these two molecular orbital which are different in energy. Okay, whereas here is same energy. Here is different in energy, and this we call it as valence molecular orbitals. This region is called as valence molecular orbitals. Okay, so now 2s combined to form sigma and sigma star like this. Okay. Similarly, the 2p combined, okay, so let me draw it here so that like it is 2p. Okay. So 1s, 2s, sorry, let's not, I'm not drawing the 2s, sorry. It has 5 electrons. 2p has 5 electrons. So the diagram is wrong. Okay, it has only one, like one electron, one of the p orbital. Okay, they combine. Okay, so now when they combine, okay, this is p orbital. When they combine one set of p orbitals, like one p orbital from here, one p orbital here, try to form a sigma bond. We'll try to form a sigma bond. Okay, so that is sigma molecular orbital. Okay, sigma orbital. Okay, sigma star. There is remaining two p orbitals, right? So one orbital from here, one orbital from here combined to form two orbitals, that is sigma and sigma molecular orbital, that is sigma and sigma star. Similarly, the remaining two from here, remaining two from here, so totally 4 will combine to form, okay, pi orbitals like pi bonding and pi star anti-bonding, that is like this. Okay, so this is a one pi orbital from combination of one of p orbital from here, one of the p orbital here, and another is from here for 1p here. Okay, so 2p from here, 2p from here, so totally 4 molecular orbital. In that 2 are pi orbital and 2 are pi star. Okay, so this is pi and this is pi star. Okay. Now, when I fill the electrons, so for example, here I have two, here sigma from the 2s, so you can basically combine and to have like 4 electrons, 1, 2, 1, 2, 1, 2. Now I have 5, 5. Now let's say I fill the electrons. 1, 2, next is 3. Okay. Now the question is whether I have to put the third electron here or here. Okay. Since you see the diagram, you can may go with saying anything, but the actually is once you put this one, if there is a similar orbital, there is an orbital of similar energy, you have to put the next electron in that. Okay. Then you come for pairing like this. Okay. You keep that in mind. So first you have to fill one orbital, one electron, one orbital, molecular orbital. And if there is another molecular orbital of similar energy, put the other one. Then you come for pairing. Similarly, like this. Okay. So this is how you should fill the electrons in molecular orbital. Okay. So this is for fullerene. Similarly, let's say another example, that is like from heteroatom HF. Okay. Hydrofluorine. Okay. Now I have hydrogen 1s1, fluorine 1s2, 2s2, 2p5. Okay. So the obvious, all like guess my people generally go with this like, okay, this is has s orbital and this has s orbital, they may interact. Actually, it is not the case. Okay. Why is that? Because, okay, now let's say I draw the for fullerene. Okay. So 2p, 2s. Then I have oneness. So I have oneness 2, 2s, 2, 2p, 5. Okay. So this for fullerene atom. Okay. Now I have hydrogen atom. See, this is oneness, 2s, and 2p. So this is with respect to energy level. Now, if I try to see what is the energy of oneness, okay, of hydrogen, the energy of oneness in hydrogen is basically close to that of 2p. Okay, the hydrogen oneness, okay, is close to that of 2p. It is not close to that of oneness of fullerene. Okay, so basically it will interact with this 2p orbital. Okay, so now in this case, this one, okay, will be similar in energy in molecule HF. It will be similar in energy. So this basically becomes the core molecular orbital. In this 2s 2p becomes the valence molecular orbital. Again here you have remains same. Okay, in this case this will be like a non-bonding orbital. Here one of the p orbital interact, okay, forming a sigma and sigma star. Okay, and this s interacted to form this sigma and sigma star with one of the p orbital. So there is remaining two p orbitals that will remain as a non-bonding orbital. It will be similar to that of. So this is a non-bonding orbital arised from the two p orbital, and this is sigma and sigma star. Okay. So now I have one electron here. Okay. So totally I have 6 electrons. So if I fill it 1, 2, okay, then 3, 4, 5, 6. Okay, this is the molecular orbital diagram for HF. Okay, this is the molecular diagram for HF. Okay, so similarly, like one can also, so what I showed you is just a orbital and how we are filling the electrons. Okay, so but when you do the studies like using the quantum mechanics, one can also get the shape of it. Okay, so to give you an idea. Okay, so this is how one can also study the orbital, how it looks. Okay, the lobes, and they have nodes. The lobe is this where this electron density is around, is there like lobes. Node is the point where the psi becomes zero. Okay, so one can find how the lobes and looks for each orbital. Okay, like molecular orbitals. Okay, after like this interaction. Okay, so one can also find that shape and size. Okay. So now, in this molecular orbital, we saw there are like sigma bond, there's bonding, anti-bonding, okay, which are sigma, sigma star, pi, pi star, and non-bonding orbitals. This all we saw, okay. Now, next, what we are going to see is a bond order. Bond order. Initially, it was like in even like a valence bond model. It was calculated, okay, based on number of bonds it can form between the two atoms. Okay, bond order is basically nothing but number of bonds between the two atoms. Okay, pair of atoms. Okay, so for example, in oxygen, it was based on valence bond theory. It was assumed that this basically has two bond order is bond order is 2. There are two bonds, okay, from the valence bond theory to the structure. It was assumed that this was all a bond at 2, and there are no unpaired electron, and assume that it is diamagnetic. So diamagnetic is basically like to do the magnetic property. Okay, if there is no unpaired electron, we call it as diamagnetic. Okay, so it will now when they did the experiment, okay, when they did the experiment on so this is O2 molecule. They found that, okay, it is not diamagnetic, it is rather paramagnetic. That is, it has unpaired electron. The experiment suggested that it has oxygen is paramagnetic. Okay. So now to understand that, okay, we can draw the molecular orbital, okay, for oxygen. So now I am going to draw the molecular orbital for oxygen. I am going to draw only the valence molecular orbital. Okay. So valence molecular orbitals are 2s and 2p orbitals. Okay. So it has 1s2, 2s2, 2p, so 2s2, 2p, 4. So 2s, 2p. Okay. So this of oxygen. So how it is going to be for molecule. So this will form sigma, sigma star. Okay, sigma, sigma star. Okay. Similarly, here it is going to buy. So these are both are 2p, right? So you know, like this is sigma, one of the p orbital combined to form sigma, sigma star. So the remaining two p orbitals, they form pi and pi star. So now I have to fill the electron. So here it is 1, 2, 3, 4. So 1, 2, 3, 4. See here I have 4 plus 4, 8. So 1, 2, 3, 4, 5, 6, then 7, 8. So it has two unpaired electron. So molecular orbital theory suggests that this is two unpaired electron, whereas valence bond theory it suggested there is no unpaired electron and it is diamagnetic. Okay, so this is the advantage of molecular orbital theory over valence bond theory. And also remember like how we are filling the electrons. Suppose if you fill it by mistake, like putting two electrons here, then you cannot figure it out. So that is why if there are two molecular orbitals of similar energy, you have to first put the electron in one orbital, then go for the next one, then only you have to come for combining the electron. Okay, so remember that rule. Okay, so now this tells that it is paramagnetic. Similarly, one can calculate the paramagnetic. Okay, one can calculate the bond order also. The bond order is nothing but number of bonding electron minus number of antibonding electron divided by 2. Okay, so in this case what I have is, okay, 1, 2, 3, 4, okay, 5, 6. So this is also bonding. Okay, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I have 8 minus antibonding 1, 2, 3, 4 minus 4 divided by 2. Okay, so it is my 8 minus 4, 4 by 2. Answer is 2. So it tells the bond order is 2. That it tells that the oxygen has 2 bonds. Okay, oxygen has 2 bonds. Okay, so this also can be explained by the molecular orbital theory. Okay, in a more clear way than the valence bond theory. So the valence bond theory, okay, failed to explain the paramagnetic behavior of oxygen, whereas molecular orbital was able to explain the why it is paramagnetic in oxygen. Okay, it also tells, okay, so like I said, like bonding, okay, try to form a molecule, like try to form a bond between the atoms and form a molecule, whereas antibonding try to undo it. Okay, so to give an answer for that, okay, let's say helium. Okay, we know helium. What is the helium configuration? It is 1s2. Okay, now if I try to draw the molecular orbital, okay, I can simply draw molecular orbital like this. So this is helium, 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 1s, okay, sigma star. So I have 1, 2, totally 4 electron, 1, 2, 3, 4. Okay, so this is a molecular orbital for helium, but whether that can exist, okay, that can be told by the bond order. The bond order will be equal to number of bonding electron minus antibonding. So how many bonding? 2 minus, here how many? 2. So 2 minus 2, it is 0. So the bond order is 0. This tells that this helium 2 molecule doesn't exist. Okay, so that we also know the helium is basically a noble gas configuration. So it will be like a noble gas. So and helium 2, that is He2, doesn't exist. Okay, the molecule, helium molecule doesn't exist. It basically remains as an atom. Okay. How much time do we have? Similarly, I would suggest you to go and have a bond order calculation for lithium 2, beryllium 2. Okay, so these examples you can try to do like draw the molecular orbital. Okay, and see the what is the bond order. Okay, so next one example I would like to see is, so use the carbon monoxide. Okay, the carbon monoxide, again I will draw only the valence molecular orbitals here. Okay, so we have 2p from carbon and oxygen and 2s from carbon and oxygen. In carbon, okay, the energy gap between the 2s and 2p is less as compared to that of, okay, oxygen. Okay, and because of that, okay, there happens a interaction. Okay, so when they form the molecular orbital, what happens? Okay, so this is 2s forming, trying to form sigma and sigma. Okay, and because of this close in energy, there happens interaction between this p and s. Okay, the orbital found from s, and because of that, okay, what happens? This will, instead of, let's say it is supposed to be here, what happens? It will reduce in energy and it will be like this. Okay, and similarly, okay, so it interacted. Okay, it reduced energy. Similarly, what happened, if you remember here, okay, in oxygen also you have this sigma down, right? Okay, because of this sp interaction, what happens? This sigma will go in higher in energy, and hence what happens? It will go higher in energy. Okay, and the pi will be lower in energy. If you see here, the pi sigma was lower. Okay, sigma was lower, here the pi will be higher, whereas it get inverted here. Okay, because of the sp mixing. Okay, we call this xp mixing. Okay, whereas the antibonding, it will be the same, pi first comes, then sigma star. Let's see, different color. So basically this sigma star, and because of the close in energy, there is interaction happens such that this sigma star reduces in energy, this sigma will increase in energy. Okay, so this is how the orbital for carbon monoxide. So this we call it as sp mixing. This we call it as sp mixing. Okay, now the electrons. Okay, it is 1s 2. Anyway, we will consider 2s. So 2s 2p 2. It is 1s 2, 2s 2, and 2p 4. Now let's fill the electrons. So it is one here, then here. Okay, now we have 1, 2, 3, 4, 5, 6. Okay, so it is like this. Okay, so now it tells that there is no unpaired electron. Okay, this is for carbon. So carbon monoxide is diamagnetic, and bond order, let's say BO. Okay, bond order is number of bonding electrons is 1, 2, here 6, so 8, minus antibonding 1, 2, here no electron, so it is 8 minus 2 divided by 2, it is 6 by 2, it has 3. So carbon monoxide has 3 bonds. Okay, so that is, we know that. So carbon monoxide has 3 bonds. Okay, so and it is also diamagnetic. So this can be explained by the molecular orbital theory. Okay, so you remember that this sp mixing happens because of the energy difference between the 2s and 2p of carbon is low. So in today's class, so we are going to see about how this orbitals interact and what are the destructive, constructive interference of what it causes to the orbital and what is the wave function. Okay, we will see about it. So begin with, okay, let's see, there is sp overlap. Okay, in any atom, let's say it can be like sp or overlap or a pp overlap. Okay, so we are going to discuss that. So we know that s orbital. Okay, so we are considering like simple like oneness. Okay, so s orbital is spherical in shape. Okay, then you have p orbital. Okay, so p orbital, let's say we have px, py, pz, right? In that, like you let's say take one. Okay, so this is s and this is p. So what is this indicate? Anyone? Students, what is this? Like when I say this region, what is that indicate? Anyone? Students? So it indicates that the sign of wave function of this p orbital, okay, this is changing. Okay, assume that this is like plus and this would be minus. I'm not saying this is plus and minus, but assume like it can be this one can be differentiated, like this plus means this is minus. So basically they are opposite. That's all. Okay, so now when they interact, okay, there is a constructive and destructive. So here it is, and this one are same phase. Say they are in phase. Okay, this one and this one are in phase. So if they overlap, okay, what you get is this. Okay, so this is what you get it. Okay, so you have two atoms. Okay, so they basically overlap. Okay, and this is how it will be. Okay, and here the wave function, okay, is equal to 1 by root 2 psi of s, okay, plus psi of p is that. Oh. Now this is constructive Okay, this is like bonding orbital. Similarly, so now the p orbital, the way it is going to interact is this side. So what does this mean? This phase and this phase, that the sign of the psi function of this one and the sign of the psi function on this one, okay, are different. Okay, this one and this one are different, as I said it. So they are different. They are out of phase. So it is a destructive interference. They are out of phase. They are going to overlap. Okay, and they overlap. The wave function is sp star 1 by root 2 psi of s plus sorry, minus psi of p z. So this is anti-bonding. So this is anti-bonding. Okay. So this is for sp. Okay. So now for pp overlap. That is p orbital of one atom, okay, is going to overlap with p orbital of another atom. Okay. So now if they overlap, how it will be? So now you have p orbitals. Okay, so here I said like pz, right? It can be py or pz, whatever, like, right? But however, it is all just the same. Only this like the wave function of this one will be of different. Like it will be, instead of pz, it will be py or px. Okay, like that. Okay. Now when it comes to pp overlap, okay, as so it is like generally we assume that like pz overlap with pz, py overlap with py, and pz overlap with pz. Okay. Now when they overlap, and generally a convention that we use also, like the pz, okay, have overlap in a manner. Okay, in pz, okay, generally assume that it is head on, or let's say this is atom A. Okay, this is 2p is at b. So 2p is at a, 2p is at b. Okay. So generally the pz orbitals are considered to undergo head-on collision. Okay. So like this, the head of this one and this head of this p orbital, they go have a collision to form these following molecules. So this is atomic orbitals. Okay. So they are going to combine to give you the molecular orbital. So in this case, it's symmetrical. It's just that I'm drawing it badly. So the atoms are here. Okay, the atoms are here, and this is the bond. Okay, this is the bond. in this case. Okay. Bond is here. Okay. So let's add it with a different color. Okay. So now here, this head of the p orbital, pz orbital, and this head of the pz orbital, they are in phase. Their sign of the wave function is basically same. Okay, so they are in phase. So when they basically overlap, what you guess is a constructive interference. And if you see this, like the probability of finding the electron, okay, around the bond is higher. Okay, so that's what it means. So you have this bond and you have this region, right? So it tells that the finding an electron in this between the bond, like between the two bonds are higher. Okay, whereas what happens here, the p is at the head is one phase, whereas this is on another phase. So when they interact, they are like basically out of phase. So it is a destructive interference, and this is how it happens. And this is the bond. So they are concentrated. The electron density is concentrated towards the and the nuclei of each atom. That is, let's say A and B, and it is not over the bond. Okay, so this is acting against this bond. So this is anti-bonding. And this is bonding molecular orbital. And if I write the wave function, okay, so now we use it like sigma star sigma, okay, and we use also another term called G and U. G stands for Gerard, U stands for Ungerard. Okay, what does that mean is it is basically to do with the symmetry of this, okay, orbital. Okay, it has to do with the symmetry of this orbital. For example, okay, if I let's say I draw this separately and tell you this. Assuming like these are like symmetrical, okay, so I'm not able to draw it correctly, but okay, so you have two atoms, okay. If so, in this, these are like this, right? So the phases of this one is different from these two, right? So now if let's say this is your x-axis, this is sorry x-axis, and this is your z-axis, okay, or let's say this is a y-axis and this is z-axis, and one we are seeing like it goes penetrating towards, like let's say the penetrating towards this orbital, that is x-axis. So the x-axis is this one. So the x-axis is basically by penetrating through this region and going on the other side. Okay, now if I rotate, okay, if I rotate it like this in z-axis, okay, or y-axis, or even x-axis, okay. So for example, the x-axis, when I'm rotating, it will be like moving in this direction, like in circular in the this paper, this whatever the one note, like let's say this is a like this is a plane. So the y is that plane. Okay, if I'm moving along the z axis, it is circulate in the yz plane like this, in a circular motion like this, it will be rotating, right? So either if I rotate through a x axis, okay, or y axis or z axis, the phase at any time, okay, is not going to change. Okay, it is not going to change. It will come back like if I do 180 degree rotation, okay, it is going to come back in the same way. Okay, suppose if I rotate it like this, so this will come here, this will go here, but however this also there, it remains there, and so the phases are not going to change. Similarly, if I rotate it like in this direction along z axis, again the phase is not going to change, and this also the phase is not going to change, and hence this is garage. Okay, whereas imagine the same thing here. Okay, so this is x-axis, here it won't change, but if I change or rotate along y-axis, it is going to change. That's why Ungara. Sorry, it will be other. So the one is bonding, okay, the constructive is bonding, and the destructive is anti-bonding. So you have this is anti-bonding, this is bonding. So this is the wave function for PP overlap when they happen along z axis. Okay. Now let's see in the other axis. Okay, that is x and y axis. Say y axis. See, when one PZ interact like this head on head, okay, so basically then the other P, X and Y are orthogonal to this PZ, okay. So now they can't have head on head. They only can have a lateral or side overlap, okay. So you know like how it is in like PZ, okay. Like for example, like if this is PZ means, okay, this is along the Z axis means, then there is py like this, okay. So if there is another atom, it has to if this has a head, like a head on head collision, okay, let's see. Okay, so this is along z axis. So if this had head on head collision and this they are y, so they can only interact laterally, side along sideway. That will be sideway overlap. Okay, so that is why we generally get this is we consider z, which is like to sigma, whereas the x and y, so even the y is like to, it is facing towards you. Okay, so x and y are considered as pi 1. Okay. let's let's put the diagram back here. So this is Py. Okay. So the Py here is basically interacting, okay, on sideways. Okay. Here, uh, mm, there is I think this is something wrong. Okay, so let's say don't think this color. Okay, don't worry about this color. Just go with this shaded where I'm shading it, because there is something wrong in the picture. Okay, so this shaded is what means the side for wave function. Okay, the phase is here. This here are same. Don't go with color. These are same. Whereas the sign of um, these two are same. Now in this one it comes here, the sign of this one is different from this one. Okay, and sign of this one is different from this one. Okay, you see the shaded one. Okay, don't go the color. Okay, now when they overlap, okay, these two are in phase and these two are in phase, so they will have consecutive interference. Whereas here this is in out of phase with this one, and this one is out of phase with this one, so they have a destructive interference. So when they interact, okay, basically this is how the orbital you have, the pi orbital. Okay, so the basically you can see that electron cloud will be are above and below the bonds. Okay, so that is the pi bond. Okay, whereas here it is not concentrated on the bond. Okay, it is more of towards the nucleus, okay, of the individual atoms. So this is antibonding. So this is bonding and this is antibonding. Similarly, it can happen in x-axis as well. Okay, so this x-axis is shown in a little different in way, so that like you can imagine it is towards you. So okay, so the p orbital is okay, so it is like something like this, but you are viewing it from this direction. Okay, so you are basically viewing the p orbital from this direction. That's why it is shown like this. Okay, now when they interact, okay, now this is the way it is. Sorry, still you are viewing, okay, along this direction. That is the it is penetrating the this plane. Okay, let's say this is the one note is the YZ plane. It is penetrating towards the plane, the x-axis, and you're viewing from it. Okay, the bond is shown so that like in a like a transparent, like which is in between these two region. Okay, this, let's say this is the two face of pi bond. Okay, the bond is in between these two faces, just it highlighted so that you can see it. Okay, now it is similar to this one, but now we are viewing it from this axis. Okay, rather than viewing it like this, you are viewing it from this axis, that is like x-axis. Okay, so this is how we are will be seeing it, and here it is a constructive and here is a destructive. Okay, so this is bonding and antibonding. So kind of like Py and Pz are similar, okay, except that the direction is different. And so the wave function also, just that you have to change the it is x-axis here and it is y-axis here. Okay, it is shown like 2pya. It is nothing but they are trying to say like 2pya. Okay, sine 2pya. Okay, so these are the SP overlap, PP overlap. Okay, in PP overlap you have three types like PX, PPZ, and PY. Okay. yesterday when we were talking about carbon monoxide, okay, we also told you that, like I also mentioned you that there is the energy difference between the S and 2p are low, okay, and they have a, sp interaction, like sp mixing, okay. So that sp mixing can happen in atoms, right? Here shown here, from like until nitrogen, okay, you can basically see the sp mixing, whereas in oxygen, that's why when we drew the oxygen molecular orbital, okay, there was no sp mixing, and the sigma of the p orbital, the sigma formed from the sigma orbital, molecular orbital formed from the p orbital of the atom, remain like low, and pi orbitals by like this in oxygen. But when we went for carbon monoxide, okay, when we went for carbon monoxide, we basically do it like the sigma orbital is like this, okay, so sigma star, pi star, okay, like this, okay. When we went for carbon monoxide, the sigma came above, okay, then sigma star, pi star, pi. So the sigma here came above because of the energy difference between the 2p, okay, two sorry, 2p and 2s, okay, are low, okay, it's not, and also their energy the level levels are also matching with the 2p orbitals of oxygen, okay, so they had a overlap easily. So that is a sp mixing in this compound, that's why. Now seen all this thing about a molecular orbital, okay, there is one more phenomena, okay, which was easily able to explain by the molecular orbital diagram or molecular orbital theory. Those are conjugation. That is the case where you had a alternative double bond and single bond. Okay, in the compound that had alternative double bond and single bond, okay, the molecular orbital theory was able to explain it in compared to the valence bond theory. The valence bond theory failed to explain it. Okay, so the like what valence bond failed to explain in oxygen, okay, where it is like paramagnetic. Similarly, it also failed to explain this conjugation. Okay, so this way, like molecular orbital theory also plays importance as compared to that of valence bond theory. Okay, and basically we started using the molecular orbital theory. So here, when we are going to talk about this conjugation, it generally like this alternative double bond and single bond, it happens in the organic compounds. Okay, so like we begin with a simple molecule ethene, so as a C double bond C. Okay, so this compound has a like other like our orbital overlap, but we are not going to discuss those things in detail, but we are only going to consider the p orbitals in this compound. Okay, so here this you have this carbon has a 3 p orbitals. Okay, so px, py, and pz. Okay, so the two orbitals, okay, two p orbitals of carbon, okay, they interact. Okay, the two carbons of the p orbital, they interact and form the sp2 hybridization. Okay, so basically that carbon has okay the two p orbitals, there's three p orbitals, okay, and so this is a sp2 hybridize. In that sp2 hybridize, okay, one is interacting here, okay, and the other p orbital is interacting here, and the other orbital form a sigma bond here. So sp2 is trigonal, right? Trigonal geometry sp2 hybridization. So it will be like, okay, let's. Still it is not trigonal. Okay, so it's like a trigonal geometry. So in this one is hydrogen, the other is hydrogen, another is sigma bond. Okay, another is this carbon. Okay, so it is another carbon like sp2, like this carbon. Okay, so this is carbon, this is hydrogen. Okay, and there is another carbon interacting like this, and this is what you get it. Okay, so now in this, okay, we are going to consider the remaining p. So it is sp2. Okay, so there is one another p orbital here in the carbon. Okay, which is not involved in the hybridization. Okay, so there is another p orbital. Okay, in this carbon and in this carbon. Okay, let's see. So this p orbital has one electron in it. This p orbital has one electron in it. So each carbon, okay, has one p orbital with one electron in it. Okay, so now they are not involved, okay, in any bond right now. Okay, now they are going to interact, okay, and form a pi orbital. Okay, when they form the pi orbital, what we are going to end up in getting is like two p orbital combined to form molecular orbital. So how many p molecular orbital you will get? You will get two molecular orbitals. Okay, so one is like this. That is, they are in phase. The other one, this one is constructive. The other one is destructive. So this is antibonding. This is bonding. So this is pi star we call, and this is pi. Okay, so we saw that like this basically has a electron cloud, okay, above the bond. Okay, now these are the simple molecule like ethane. Okay, so now if I go for a little bit bigger, okay, like 1,3 butadiene. Okay. So this is 1,3 butadiene. I have carbon 1, 2, 3, 4. Okay. So now I have alternative double bond and single bond here. I have alternative double bond and single bond here. Okay, and you see the single bond is between C2 and C3. Okay, so when I have a single bond, CC single bond, okay, I have another situation that when there is a CC single bond, they can undergo rotation. Okay, the CC bond can undergo rotation such that this entire unit will keep moving with respect to this one. Okay, so so like let's say this is a CC bond. Okay, let's say this is a, let imagine that. Okay, this is something like A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Okay, so C, D like this. Okay, so this CC bond can undergo rotation such that the position of this can change. Okay, like B, A, it can D, C. Okay, so they undergo rotation and can change. This is why, like, you might have heard the structures like staggered structure, eclipse structure, right? So that's what I'm trying to say. Okay, so you have that CC rotation is possible when you have a C single bond C. Okay, so that has one has to expect that. So when we have this compound, the expected are again by valence bond theory. Okay, this C2 C3 as sigma bond, single bond. Okay, sigma bond, and should undergo a rotation. So sigma bond is should be like similar to that of 154 picometer. Okay, the carbon-carbon single bond, the distance is 154 picometer. So the expected is this one. Okay, so this is what expected according to valence bond theory. Okay, but the experiment when showed that the C2 C3 bond length is 148 picometer. If you actually see the CC bond, single bond, if it is 154 picometer, if it is C double bond C, the bond length is 134 picometer. Whereas this one, actually the experiment C2, C3 showed that it is 148. It is neither like a C double bond C or neither like a C single bond C. Okay, it is neither like single bond C nor like C double bond C. Okay, so so this showed there is a difference. And another factor is that there is a rotation barrier. Okay, this is C2 C3 bond has a rotation barrier. Okay, so if it is a C single bond C, we assume that it should undergo rotation. Okay, along this, like we can have rotation, have staggered and eclipse structure, but that is not seen. So this that have a rotation barrier in this. Okay, so this was not able to explain by the valence bond theory, whereas now molecular orbital theory, okay, try to explain it, okay, by having the similar approach what we had here for the simple molecule E3. So now let me put the image directly so that like we can save time. So now you have 4 carbons. Okay, so you have 4 carbons. All are sp2. So this is sp2, 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 sp2. So you have 4 carbons. There is each carbon has 1 p electron. Okay, with one p orbital with 1 electron each. Okay, so we are going to draw the pi orbital using the molecular orbital theory. So if we do that. Okay, I think this one. So you have 4 carbon. Okay, so each carbon has a 1 p orbital with each one having one electron. So if we draw the pi orbital for that p, okay, so you have four. So you have four molecular orbitals. Okay, now, so now I can have like the one here. Okay, pi 1, okay, pi 2, these are like bonding, and this is anti-bonding. Okay, you have pi 3 and pi 4. So if you see here in the pi 1, okay, the all the interaction is basically here is like constructive, and all are in phase in the above and below. Okay, they are all are in phase in above and below. Okay, and here if we come, you can start seeing the node. Okay, so if I draw the wave function, it will be like this. Whereas if I come here, it will be like this. Okay, so there is a one node here. Okay, similarly if I draw for this one, okay, it will be having two nodes. Okay, it has two nodes. Okay, similarly the pi 4 will have four nodes. Okay, sorry, three nodes. So this is two nodes, this is three nodes. Then we have, okay, so this is having no, 0 node, 1 node, 2 nodes, 3 nodes. Okay, that is the sign is changing. Okay, now coming back here, okay, the pi 1, okay, the pi 1, if you see, they are in phase, and between carbon 1, 2, 3 and 4. Okay, so this tells that the electrons are basically delocalized, okay, between C1, C2, C3 and C4. Okay, so there is a delocalization of electron, or the electrons are spread out through the 4 carbon. Okay, so this phenomena, okay, is called as conjugation. Okay, and this is like basically the conjugated pi bond. So the 1,3-butadiene, okay, is basically considered to have a conjugated pi bond. Okay, that is the electron, okay, or delocalized, okay, between carbon 1, 2, 3, okay, and 4. Now, if you also like remember when we drew the particle in one-dimensional box, okay, the wave function, okay, if I remember, like let me show this. So this is what the image I showed you, how the wave sign function will be having, like a n for any particle in one level, say n equal to 1, n equal to 2, n equal to 3, like this, right? So now this one and this one look similar, right, if you remember. So now I can even use that same particle in one-dimensional box, okay, and calculate the energy difference. So now this, so this is, you imagine like pi 1, pi 2, pi 3, pi 4. So it is similar to that of particle in one-dimensional box. Okay, so I have pi 2, okay, pi 3 is star, okay, so this pi 3 star. So this is my HOMO and this is my LUMO. Okay, this is my HOMO and this is my LUMO. Okay, so now I can use the formula, okay, that is E is equal to n square h square by 8 m a square. So here n is, we are going to see the transition between n, which is 2 and 3. Okay, that is 2 and 3. So this is n equal to 2 and 3 we are going to see. So we are going to calculate the delta E between the 2 and 3. Okay, so if I say the delta E, okay, it is E3 minus E2. So here only variable is n square, right? So if I n, okay, so if I put n separately, Okay, so the n is here is n square. Okay, so 3 square 9, 2 square 4, then we have this h square by 8m a square. Okay, so which is around 5 h square 8m a square. So you can also convert this into lambda, so it is delta E, sorry, h c by delta E. Okay, so if I calculate the lambda, okay, for this one, okay, the lambda max, okay, will be around 204 nanometer. Okay, so where you have know that like this is a Planck constant, speed of light, and a is considered as like the cc bond length. Okay, and then you have this m, okay, mass of the electron. Okay, so if you put those terms, what you get is 204 nanometer, and the experiment value is around 217 nanometer. There is a small difference, okay, but it's close matching. The small difference is basically like this particle on dimensional. We don't consider anything like a non-linear because this molecule is non-linear, so we don't consider that fact. Okay, and there is also like a issue of like considering like C single bond C or like C double bond C. That difference is also there. Okay. So this becomes like also like how one can utilize the particle in one-dimensional block, like an example for particle in one-dimensional box, we can consider this. Okay, so I talked about this conjugated pi bond. Now, let me show on another example. So I have this hydrocarbon, okay, 1, 2, 3, 4, 5, 6, 7. Okay, there are 7 carbons. Okay, now tell me like whether this entire molecule is conjugated pi bond. Okay, so for a conjugated pi bond, okay, you should have a alternative double bond and single bond. Okay, so let's see whether it is. So single double bond, I have single bond, double bond, single bond, but I didn't have a double bond here between C5 and C6. So basically the conjugation is get broken here, like it can't have a conjugation after this. So it can have a conjugated between 1 to 4. So this can behave as a, this two can behave as a conjugated pi bond, whereas this pi bond is kind of basically like a isolated pi bond. Okay, so remember that for a conjugation to occur, okay, it should be alternative single bond and double bond, okay, where which was not there here, and hence this only can behave as a conjugated pi bond, whereas this one can behave as a isolated pi bond. And if you measure the stability of this one, okay, like not this molecule, the 1,3-butadiene, okay, if how it will be like if compared to like a non-conjugation, the energy seems to be much favoring when it is like the energy of the molecule seems to be lower when they have a conjugation. Okay, so the conjugation not only exists like where you have this double bond, right? Like it can also brings pi bond in having the CC double bond. So it can also have the involved when you have like oxygen, nitrogen, the pi bonds also, okay, with the carbon. Now the next step, okay, seeing this alternative double bond and single bond in these linear molecules, okay, let's go for a cyclic compound. That is benzene. So now benzene, if you see, you have 6 carbon, okay, and they have alternative double bond, single bond, similar to that of what we saw in 1,3-butadiene. Like what for the conjugation we saw, they have alternative double bond and single bond. Okay, so some, like basically again, like there is like a possibility of this delocalization here. Okay, but now talking that, okay, there is additional like stability to this aromatic compound, okay, in compared to that of, okay, 1,3-butadiene. Okay, so that gives some stability here as compared to that one. What are those factors? Okay, so one is like delocalized to say this resonance. Okay, next is like the they being cyclic, okay, and planar. Okay, so we are going to see that with an example. Okay, so if I draw the pi orbital for this, okay, I have 6 p. Each one having one electron, 6 carbon, so each one have a 1 carbon, so I am going to have a 6 pi orbitals. Okay, if I draw the 6 pi orbitals for this, okay, so I'll have pi 1, pi 2, pi 3. Then I have pi 4 star, pi 5 star, and pi 6 star. So these are antibonding, and these are bonding. So I have 6 p electrons. So if I fill it, 1, 2, 3, 4, 5, 6. Okay, so 6 p electrons are filled here. Okay, so this is the molecular orbital of this compound. Okay, let's take another example. Okay, where you also have this alternative double bond and single bond. So this compound also has an alternative double bond and single bond. So this has again have 8 carbons. Okay, 8 carbons, 8 p orbitals. Okay, if I draw the molecular orbital for this one. Pi 1, pi 2, pi 3, pi 4, pi 5, pi 6, pi 7, pi 8 star. Okay, so in this, okay, these 3 are bonding, whereas the pi orbital pi 4 and pi 4 the energies are similar to that of this, okay, p orbital, so they basically consider as non-bonding, and these are bonding molecular orbitals. Okay, now we have 8 electrons. So if I fill that, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now if I compare this molecular diagram and the molecular diagram of benzene, I can see that this is like a entire bonding orbital is filled with electron, whereas here, in addition to the bonding orbital, there is a 2 electrons in the non-bonding orbital. So this something like similar to that of noble gas, okay, where they have the stability due to the orbitals, okay, by having the like a full cell of electrons, okay. Here benzene has all the electrons in the bonding, okay, whereas in addition to the bonding, they also have non-bonding. So this also plays a major role in the stability, okay, and gives the that's like we basically say like it is more stable, okay. Now, coming along that line, what are the factors that determine the aromaticity? So when I say an aromatic compound, what are the factors that determine that? So that gives the stability, okay, for these compounds, okay. So that is the molecule or group must be cyclic. The ring must be planar, and each atom in the ring must be sp2 hybridized. Okay, so this itself, like we can see, like with the help with this compound, okay. So we can see that like here it is not it is a ring structure, but however it is not planar, okay. So that it basically gets eliminated, that it's not aromatic compound. So in addition to all the above three, okay, so the number of pi electron in the ring must be equal to 4n plus 2, where n is any positive integer, like n equal to 1, 2, 3, like that. So n equal to 0, 1, 2, 3, like. So suppose if n equal to 2, okay, so 4n plus 2. If n equal to 0, it is 2. It is n equal to 1, it is 6. Then n equal to 2, 10. So like this, you can have 14, 18, 22, and so on. Okay. So now for a aromatic compound, okay, it should have this 4n plus 2 electrons in addition to this above 3. This 4n plus 2, okay, is basically called, okay, this rule is called Huckel's rule. Huckel rule, okay, is basically formulated by a scientist Huckel, okay. So he described that like the aromatic compounds should have 4n plus 2 pi electrons. Suppose if it is not having 4n plus, let's say we have an example, the benzene itself. Okay, so the benzene is cyclic, planar, each carbon is sp2 hybridized, each carbon in the ring, okay, and it is having 6 pi electrons. So it is matching with 4n plus 2, where n equal to 2. So n equal to 1. Okay, so 6 pi electron. So this is aromatic. Suppose I have a compound like this. Okay, so in that case, okay, I have this all three factors like cyclic, planar, and each carbon here is okay sp2 hybridized, but instead of 4n plus 2 I have 4 pi electron. Okay, so it is not matching 4n plus 2 group. Okay, so it is not aromatic. It is not aromatic, but there is another thing called anti-aromatic when it has 4 and pi electron. Okay, so it is cyclic, planar. Okay, and you have sp2. So when I say this sp2 hybridization, it's also mean like they have conjugation. Okay, conjugated. Okay, the pi bonds are conjugated. Okay, so then 4 and pi electron. So this called anti-aromatic. So this compound is anti-aromatic. Okay, so like this you can say aromatic compounds, anti-aromatic compounds. If they don't belong here, okay, we can call as non-aromatic. So let's say any linear, for example, like this. Okay, this is doesn't follow any of this, so they are non-aromatic. Okay, so you have these three categories: non-aromatic, anti-aromatic, and aromatic. Okay, so you remember this. Okay, when you describe any given molecule is aromatic or not. Now, let's discuss about a compound like does anyone know what is this compound? Students, anyone know what is the name of this compound?
Pyridine.
Yes, is we say pyridine. Okay, it's like pyridine. Okay, and this one is pyrrole. Okay, so sorry, pyrrole. So pyridine, pyrrole. Okay, we say okay. Now the question is, are they aromatic? Anyone know whether it's aromatic or not? They are aromatic. Okay, even though like here it is like 6 electron, you can say directly okay, it is matching everything and it is like aromatic. But here it is like having only 4 pi electrons. Then how we saying this is aromatic? Okay, that's a question comes. So the understanding here is that when you go for a compound, let's say we begin with the pyridine itself. Okay, when we say pyridine, okay, so this is the how the pyridine orbitals are. Okay, so now we have 5 carbons. Okay, that's why like 5 carbons. Okay, they have p, each one has a p p orbital with 1 electron in it. Okay, and in addition you have this nitrogen. Okay, so nitrogen is like 2s, like 2s to 2p3. Okay, so now they basically has to be as sp2. So this nitrogen has to be as sp2. So here you have this nitrogen in a sp2 configuration, and one of the orbital of this sp2, okay, one of the lobe of this sp2 orbital, okay, what has like two own lone pair. Okay, so that lone pair, okay, will be like this, doesn't get involved in the ring. Okay, and now you have this two sp2, which is like basically one with the bonding with carbon, the other one bonding with the other carbon here. Okay, the adjacent carbons, and there is one p orbital with one electron. Okay, there is one p orbital with one electron that get involved in the conjugation here. Okay, so now you have each one has a one p orbital with one electron. Okay, similar to that of benzene here. Okay, and they basically has basically 4n plus 2 pi electrons, and other things happens like, for example, like planar, cyclic, and sp2 hybridization. Each atom is sp2 hybridization, and you have 4n plus 2 pi electron. Okay, and the delocalization happens, and hence basically you have this aromaticity in this compound. Whereas the other one, the pyro, if we try to think in the same way, okay, we may say that it's not the aromatic. But what happens there is actually, okay, again you have 5 carbon, okay, and you have this nitrogen. Here the nitrogen, okay, again it is undergoing sp2 hybridization, but the difference with what happened in this pyridine is that with respect to that in this pyrrole, you have sp2 hybridization, but each orbital of lobe of this sp2, you have one electron here, whereas the pz, that is one of the p orbital, okay, where it came here like this, here what it has is the 2 electrons. So this will be like a lone pair electron. Okay, so now these have 3 lobes, so each one interact with the each on adjacent atoms. So for example, these two will be bonding with the neighboring carbon, and this one will bonding with the hydrogen. Okay, so as shown here, and you have this p orbital with 2 electron. So now if you see, this is having 1 2 3 4, okay, 4 carbon, and you have like plus 2 electrons from here. So this totally like 6 electrons. So again 4 and plus 2 is satisfied, and they have like delocalization, and hence this is basically the aromatic compound. Okay, so hence this is also aromatic compound. So like this, you can also I'll just give you like a homework. Okay, you can have a go and look in the later. Okay, so compounds like you can go and find what is this compound, like whether they are aromatic, anti-aromatic, non-aromatic. You have to see and find out. You can take it as a homework. And I drew the benzene like a molecular orbital, okay, without showing you how the orbitals, like I just drew like a standard. So okay, so this is basically the benzene molecular orbital. Okay, how it is. Okay, so here you see like pi 1, so they all are in phase. Okay, so then you have nodes start appearing at pi 2, pi 3, pi 4, pi 5, pi 6, like this. Okay,